thanks for having invited me to this very detailed technical and scientific event. I will not go into scientific details. I will talk about energy transition and why materials, especially those who are called critical materials and supply chains, are so important and then can be critical for the achievement of the whole transition. So I'm co-chairing ETIP SNET. ETIP, I will explain shortly what is ETIP SNET. You can see this nice looking graphic, which was the first deliverable of ETIP SNET. It is a vision of how the energy system should look like in 2050, let's say in the future. We will then go to, where is the pointer? This is the pointer. What is energy transition, and particularly what is energy transition for the power system? And so which critical materials and which processing and their supply chains are impacting this, with a focus then on power grids and batteries and electric vehicles. All of this to say that we do expect from the science of materials still a lot of innovation to make this possible in the most sustainable way. So in Europe, there is a set plan among the many initiatives for innovation and for competitiveness. Inside the set plan, we have several ETIP. ETIP stands for European Technology Innovation Platform. There are many of these which are specifically, for example, for batteries, photovoltaic, geothermal. And then there is one, which is the one I co-chair, ETIP SNET. SNET means Smart Network for Energy Transition. So we are cross-cutting horizontal, and we have contacts with all the others. What we do, this has been founded by European Commission, which is still chairing the governing board, and it is pulling together all the actors of the energy sector, from system operators to research, academia, storage operators, manufacturing of equipment of ICT, and also generators and consumers. So all the stakeholders who are represented, there are more than 30 representatives from all these stakeholdership. And the mission is to have an integrated approach to innovation and to identify and advise the European Commission about the priorities in research, development, and innovation. And also prepare consolidated stakeholder views when European Commission asks us. We have 6 working groups. I am also sharing this one, which is about mainly grids and system view. What we bring about is the system approach, and we have more than 200 experts actively involved in these working groups from all the stakeholders. This is one kind of deliverable, the vision, which was the first one. And then we have done roadmap and implementation plans. And these are overarching documents. This one is under review. Roadmap will be now in 2025. We will issue an updating of it. And then we have a lot of single focused papers, typically white papers. Sometimes they're also position papers. For example, one of the last I was responsible for is the impact of hydrogen on the power grids. So let's see now the energy transition. I will give some flashes. In our field, most of the things are a consolidated basis, but maybe here in this room, it's good to have a general overview. First of all, energy, maybe energy, water and food. There is also energy, water, food nexus that we are also analyzing. Energy is essential for human progress. And you can see that there is a direct connection between the Human Development Index and the energy demand per capita. This both for domestic, residential, industrial use, all these kind of uses. So we need energy to be accessible, affordable by everyone. And the big issue in the last years and still the years to come is the decarbonization. This is no-brainer, although there can be bumps on the road to decarbonization, like political attitudes, what we see in this period, that some countries are withdrawing from the previous commitments. The point is, we can say many things about decarbonization, but I like this graphic because it shows that we have a limited amount of carbon or greenhouse gases which can be accumulated in the atmosphere, after which we run into irreversible processes, physical and chemical processes. And this carbon budget is almost exhausted. So the issue is not so much how we are going to decarbonize. We know how, but how fast we can reach it. If we continue to delay, then to not to go to irreversible phenomena, which we have much more difficult task to achieve. So every year we wait to really go in this direction, and the less it will be achievable, and we have to prepare to adaptation to climate change and no more to avoid it. So it's what is called the carbon crunch. The power sector in which I work is already well oriented to decarbonization. This is not considered an issue anymore, also because economically it has been the most convenient using renewable sources and decarbonized processes in the use of energy, decarbonized generation and decarbonized uses of energy is already become mainstream. But other sectors like heating and transport are the next elephant to be addressed. So you see here that generally speaking, already new investments in generation are almost only renewables, so no incentive more or less is so important, except maybe to have a higher penalization on CO2 just to accelerate, because I stress the fact seen in the previous slide that the issue is not how to achieve there, but how fast. Oil mainly goes to transport, and transport we know is going to be decarbonized through electrification or through decarbonized molecules. Gas is considered a traditional fuel only because respect to oil and coal, it has less CO2 footprint, but still fossil has to disappear. So in the end, it will disappear. Coal is the big one which has to be fought against. And there are still countries like China, India, but also United States who are still building coal plants. Nuclear will help because it's decarbonized, but the future is uncertain because it has other kind of issues. So you see here, you can find many graphs like this, but what is sure, in every graph, you will see solar and wind soaring. So this is another key point. Focusing on power sector is not enough to reach climate goals. We need power generation, and we are doing it. We need the transport, to decarbonize transport, to decarbonize industry. The industry which is using fossils will have to use non-CO2 emitting sources. And the building stock is also very important because buildings are consuming a lot, especially for heating and cooling. So we will use electrification of final uses, but also hydrogen. We will increase bioenergy and other instruments like reforestation, carbon capture and storage. So renewables are part of the solution, but they are not enough. We need also to have more efficient system, which means well, it cannot be closed there. We need carbon capture, we need nuclear, we need also some change in behaviors. we need all of this. Otherwise, if you remember the carbon crunch, we will be crunched. So there is a lot of debate around, we don't want CCUS because it means keeping, maintaining the use of fossils. Somebody is against nuclear for other reason. The fact is that we need all what we can, at least in the next years. Then in the mid to long-term future, we can decide what we keep and what not. Electrification seems to be the first choice because there are no energy conversions, so it is the most energy efficient one. But some final users cannot be electrified, and so we have to use other ways, like, for example, the hydrogen. So we expect from the scientific community and technological innovation, still innovation in all the sectors that you see here. So we need to deploy at world level a lot of efforts in almost all the sector of energy, because we need all of them now. So the legacy energy system was based mainly on oil for transport, coal for electricity generation, and natural gas for electricity and for residential. And then, of course, a lot of other minor flows. This is fossil-based. This is global, but each country has a different situation. And the transport of energy from the location of production to location of consumption is mostly molecules, because electricity system, molecules are transported worldwide through pipelines or ships. And so the market is worldwide and is a liquid market, now also for gas through the liquefied natural gas. Electricity system typically started locally, then regionally, and are interconnected, interoperated only in some regions. Europe is the largest system in the world, probably the most complex and the largest system ever built by humanity, the electricity system in Europe. And then we have one in North America, one in Russia, one in China, and so, but still at India, but still covering countries or regions. So how will look like the future energy system? Just have a look at the colors here. Electricity from a minor share will become the dominant one. Most of it done without producing CO2. Oil and coal and gas will become minor. We will have increase in biomass, modern biomass, and the arrival of hydrogen and other renewables, ocean waves, other things, but still today, this will be still minor. So it is interesting to see that the energy consumption global is not going to increase thanks to energy efficiency. So electricity is becoming the backbone of all this decarbonization. And this means that oil and gas industry are facing a big dilemma. Either they reconvert, most oil companies are doing this, or there is disappearing. It is paradigmatic that reserves typically used in the balance sheet as asset now could become stranded asset if you are not able to extract them anymore, because there will be no consumption anymore. This is mostly for the transport. So you will have to keep the oil below the ground. So they say the Stone Age didn't finish because the stones were finishing. The oil age will not finish because oil is finishing. We will finish earlier than that. So we call it direct and indirect electrification. Direct electrification is where you can just change big industrial consumption from gas to electric. But other sectors, the red ones here, typically this kind of energy intensive uses or high temperature processes in heavy industry, there is no technology for having efficient electrification. So we have to do indirect electrification through hydrogen. In the transport sector, is there are a lot of efficiency to be gained. You see, this is interesting. This is an average consumption per kilometer for the internal combustion engine, and the battery electric vehicle are just a fraction of it. So there is not only an issue of decarbonization, but also our efficiency gain. And similarly will be also in, if you consider final energy consumption or primary energy consumption. Primary energy consumption considers in the balance of energy also the intermediate stages, because you have conversion. For example, from here, you have the chemical product, the gasoline, which becomes then heat, and then becomes mechanic energy, and then becomes a kilometer long. And here, you don't have this energy conversion through heat. So we can also say that the electric engine in a vehicle is intrinsically much more efficient and also much easier to maintain. No rotating parts, no lubricants, like this. In space heating, you remember the two, after power generation, transport and buildings are heating and cooling also, are the two big chunks of the elephant we have to abate. And also passing to typically heat pump, which is driven by electricity, will again not only decarbonize, but also consume less energy because of intrinsic physical phenomena utilized. Talking about efficiency, I like to stress that it is not energy efficiency, so how much energy you globally consume for having a certain final use, but there is also, which is at the base of the European principle of energy efficiency first. But we have to combine this, I would say, three dimensions. Another dimension is efficiency of infrastructure, because when we talk about energy, energy comes with infrastructures very, very costly, lasting decades, typically for gas, oil, electricity. This infrastructure can last 30, 40, 50 years, and they have very high capex. So we cannot overnight abandon one technology and the infrastructures, because we would have not efficiency in use of infrastructures. And then we have also to consider the efficiency in decarbonizing. Maybe one technology can be efficient from energy, from infrastructure, but then it's not so efficient in decarbonizing. How much I have to spend money to spend for obtaining reduction of 1 ton of CO2 in the atmosphere. So we have to see the combination of this in terms of resource efficiency, how to utilize in best way all the available resources, allocating them to the various uses, and this allocation can also change over time and over countries. So in a scheme, the future energy system will see a central role of decarbonized electricity. There will be also some decarbonized primary heat from renewables. And then all these, the challenge are all these orange call out. We need storage a lot, batteries, but other types also in form of heat. We need electrolyzers. We need infrastructure for hydrogen. So all of this means changing infrastructure, changing technologies. So a lot of investments, a lot of skills, new skills required. What is interesting to see that in all graphic, you can find a lot of them in literature. The electric grid will always be in the center of all this interaction. You see the flows are electricity, gas, liquid fuels, heat, methane being substituted by hydrogen. All of them have an interface with electricity. So electricity will be the one integrating all the energy sectors. And now, what does it mean in particular for power system? We have seen already electricity is rising. The traditional one, the light blue, but new loads are coming. For example, electric vehicle, hydrogen production through electrolysis means we have to add a new type of loads. Desalination plants are not shown here, but in some part of the world, due to water scarcity, due to climate change, will also bring new electricity demand. Another thing, you can find many graphics like this, but just to go then to the material, I want to make emphasis on the final demand, and the generation will be globally driven by wind and solar, although many other technologies are interesting to see. In some places like Iceland, geothermal can be the most important one, but wind and solar are paramount in all parts of the world and in all scenarios. So in the consuming side, we have to have deep electrification. And you can see here the yellow bar is meaning that in all scenarios and in all sectors, we will have a lot of final use electrified. You see, for example, transport is the biggest shift, but all of them are contributing. And interesting also that in terms of efficiency, how much energy is consumed for each GDP, for each economic product, is in any case declining. So we're becoming efficient also economically. And this with different patterns, but it's happening in all parts of the world. In particularly in developing economies, this is happening more sharply. So there are some parts of the world where the electricity demand is a bit more flat, but for sure, you see here, for example, India, China, and many other Africa, due to population increase and economic development, the consumption of electricity is very sharply increasing. So what is happening, if this is a scenario, what is happening to the power system? The power system is the one which brings electricity from generators to final users. Typically, it was a linear process, vertically integrated. So there is a transmission grid and a distribution grid. Now it's becoming more like a matrix where there are a lot of interfaces because, for example, generation is happening more and more near the customers. So there is a sort of logic short circuit. And a lot of distributed resources like generators and storage will arrive in the distribution network, not only in the transmission one. So this means that we have to do demand-side management, and we have to do collaboration between transmission system operator and distribution system operator. One of the most representative paradigm shifts is that since the beginning, the power system has been planned and operated in a way that generation is flexible and has to follow the load. The load is an inflexible outside variable. Now, we are going to have the opposite because generation has become inflexible only because we don't want to lose solar and wind production. It can be flexible if you curtail, if you just give away the primary energy, but since this is costly, so we have to adapt the withdrawal from the grid to follow the generation. And this we do with demand management and storage. And also with new transmission to bring energy from one part or the other of the interconnected system. Just to mention, this is very well known by electrical engineers. If we consider not the total load, but the load less production inflexible from even just photovoltaic and wind, which are called the non-dispatchable generation, the curve is becoming not like this, but like this. So they call it duck because it's more and more resembled to a duck. And the problem is you need a lot of flexibility to cater for this very high ramp. So the non-conventional generation cannot do this ramping. So what we need is flexibility. Flexibility not only transmission from typically from inside the grids, and not only from the generators, but also from storage, from demand-side management, and from other sectors. You can have flexibility in heating, thermal storage in heating, from the gas and hydrogen, and the batteries of electric vehicles can also give a bigger contribution. So the electricity system paradigm and operation is changing dramatically in few years. And you can see here, I will just drive you through The left column is why we need flexibility. And you see that in the long term, this column is mainly because of solar. Solar has to follow the daily light. And so if we want, solar is becoming the cheapest, the cleanest, but produces too much energy during midday and no energy during evening, night. So we need a lot of flexibility. You see this one. Where do we find this flexibility? Well, curtailment we would like to avoid. For example, transforming extra energy, surplus energy in hydrogen, or in other plants which can accumulate water, for example, fresh water or thermal energy. And then we need demand response, batteries, all kind. You see the right column has all the colors. Flexibility is the most important word that all grid operators are talking about today. So in the end, we can say we have in front of us a big puzzle. Starting from climate change, we have to decarbonize economy, the energy system first, electricity generation first with renewables. This means flexibility. But so new renewable can be big plants, utility scale, still connected to transmission system, or dispersed generation in the distribution grid. So substantially, flexibility means we have to move energy in space through new interconnections and to move energy in time through storage. This is energy shift. And also to move energy converting into other forms of energy. These are the three main forms of flexibility. And this means, let's just only go to this yellow call out. We have to rethink the distribution grids, which are now become active. It's not only going energy from transmission to the consumer, they are becoming active. We have to rethink the transmission grid because, for example, the protection of the lines was designed for unidirectional flow. Now the energy can flow from distribution upward, so we have to redesign completely. We have to rethink in dispatching from generation follow load to load follow generation. We have to rethink consumers, active consumers providing demand response. They have to collaborate. This is the first and most economic way of avoiding extra expansion of the grid. We have to rethink all the services also, balancing, etc. So now let's come more to the topic here of this conference, materials. This is taken from a year report. I took something, well, first of all, talking about developing new technologies, new processes, new chemicals, new materials. We typically have a trade-off, which is very tight. We look for cheaper devices, material, etc. We look for higher performance, but we have also to look for lower footprint. Typically, these three they are always one against the other. There is no magic one which accounts for the three of them. For supply chain, I took this schematic definition. We start from raw material. Raw material means mining. And then they are processed, and then they are used for for intermediate products, which in the end, this example for the battery, in the end become an instrument of battery storage, which in its turn can go typically, the highest market today is to electric vehicles. Let's forget that supply chain includes also recycling, reuse, and this, as we will see, can be very important to limit the need of new mining, refining, etc. Well, you did still some industrial processes, but at least you avoid mining. So for some minerals, the energy transition is the main driver in all scenarios. So these are some just some quantitative graphic about some key minerals for energy transition. The demand, this is the past, but it will be much more increasing in the foreseeable future. What minerals are we talking about? Copper, aluminum is typically used in electricity transmission. And then in batteries and other modern devices, we need lithium, typically for batteries, but also nickel, cobalt, graphite, rare earth. And some of them are also used not in energy transition, but the big increase is coming from energy transition. So here also, the balance between production and consumption is bumpy. So for example, in the last couple of years, the supply has expanded faster rate than demand. But this is not meaning that we have to stop to invest. It's just that the market prices will be such that there is the inverse danger that investors will stop investing because of this, because of course this means decreasing selling prices for them. But in the mid and long term, this for sure will be reversed. We see already in 2024. So an interesting aspect of the so-called critical materials is the geographical distribution. So if you see the share of raw material production by country, there is a lot of concentration. You will see here and in the next slides a lot of red color, China, but not only. Each of these has a different concentration. For example, for cobalt is Congo. And this kind of analysis is very, very important for geopolitical strategies of the country who can maybe don't want to depend on one or very few single sources. If we go not to raw material, but to refining, the concentration geographically is even higher. And here you see the red Chinese color dominating. So it's an issue of mining, but also refining. And if you can do many analyses, I just took some from recent reports from IEA. And they made also a sort of risk analysis, considering supply, geopolitical, potential this shock in the supply chain disruption. And also, this is not yet structured, but has to become, what is the impact on all the sustainability criteria from United Nations? And then you can make some quantification, but what you see is that all of them has a high risk. Risk means risk for the single company, for the single country, but here we are talking about risk of energy transition be delayed or even hampered, halted, due to issues on the critical minerals. So there is for sure a geopolitical stance. So there is an increasing attention from industry, policymakers, international strategists. We can see these days, Mr. Trump is trying to get from Ukraine the rare earth in a totally different framework. No, this is warfare, but he didn't ask anything else. He asked for minerals. Price volatility is an issue because you can see here some example of recent price volatility. For having a structured growth, the best would be some predictability, some stability in prices. If they go up and down, it's good only for speculators, but not for industry. And this would require the coordinated evolution of all the stages of the supply chain: mining, refining, manufacturing, and also the level of end users. But this would require a global coordination, a global cooperation mode, which unluckily in the last 3 years has gone decreasing. We have more wars, independence, search for independence, economic independence, political independence. So one flash on rare earths, which is becoming now very used journalistic terms. The demand is soaring, but we risk soon enough an imbalance. And here you can see some consideration about, again, a lot of needs, concentration, geographical risk, considering also that processing of this material generates a lot of environmental issues. And so some countries, they even have materials, but they prefer not to rush. Okay. Materials for power grids. We need a lot of wind, solar, heat pumps, electric vehicles. For this, we need overhead lines, cables, stations, HVDC, transformers, switchgear, a lot of things. Many of these are depending on materials. And very particular, I will finish with an example, a deep dive on storage in form of batteries. So we are talking about a huge acceleration in investments and assets. You can see grid investment, grid assets. Also because existing grids are becoming obsolete. They are very old. So we need to replace and expand both together. Grid constraints can block the transition tomorrow. So we have to invest today with anticipatory investments if the regulators allow, because these investments are typically paid in the bill through tariff. So we are thinking to have some coordinated actions within the industry, but I will skip this. And let's see this example about the materials for battery. Batteries are an essential part of the global energy system. Let's see, if we have no time, only the main messages here. You can find then in the presentation some supporting numbers and documentation. So we need batteries. And the role of storage in power system, we said if mainly for the solar, we have to store extra surplus production and use in deficit period. So you can use storages both for grid uses, both for consumers, and both for generators. All of them help to balance the system at a minimal cost. So from the scientific world, we expect innovation in the chemistries, but also in manufacturing. And this depending on the type of chemistry. There are several batteries. The focus on this slide is on lithium-ion because they are the most used, the most spread. And again, for batteries, you will see that mining, processing, basic components, and final battery cells, there is a lot of geographical concentration, and you see a lot of red color again, China. So I will skip the details, mineral, refining, manufacturing. We have to improve the supply chain, even if a raw material is not scarce or is not critical, but the supply chain can be disrupted to the detriment of energy transition. So we can do long-term agreement, we can do long-term projection of demand, we can, of course, free trade, and looking for reciprocal complementarities under a cooperative mood would be necessary, which is not the case. Free trade is just exactly the opposite is happening in these days. So we need more investments, we need more diversification, we need resilient and sustainable supply chain, resilient to external shock, and sustainable, because if you take away CO2 from the atmosphere, but if you pollute the water, then it's not a good business. And of course, there are a lot of economics and policies impacted by material. So material will be very important. That's why I was delighted to come here to this material conference to give the main final message that from the materials, we do expect a positive impact, and also from basic research and development. And yes, so you see, this is the last slide. We have the decarbonization will rely mostly on technologies which are not mature now, which are yet to come. And these are some examples. So we need the materials, but we need also supply chain, and we need the technologies still to be developed. So this will come also from the innovation world. And that's it.